So today we're going to be talking a bit about the psychology of probability. Specifically, we're going to focus in on what the concepts of probability refer to, and I say concepts because there is more than one way to think about what probability is. We're going to be talking about how people tend to think about probabilistic outcomes, why they think about them this way, and how you can use that information to improve your own thinking about probability and gain some insights into the thoughts and behaviors of others. Probabilistic thinking itself can be applied to a great many different domains of life, though I'm sure that everyone who hangs around here is often going to apply this type of thinking to their games of Hearthstone. We're going to talk about what decks are expected to have the best win rates, which builds of those decks are the optimal ones because of how the card choices increase your probability of winning. We're going to talk about the chances for us to obtain certain random outcomes within a match, and we're going to combine all of this information to explain why we're very smart, we make all the right plays, our opponents just got lucky when they win, and the game is fundamentally bad and for children. So when it comes to probability, people are ostensibly going to get a lot of things wrong when they're thinking about probability. But as we're going to see soon, there's actually a certain logic that underlies these mistakes. And once you understand this logic, it's going to make the mistakes seem less like mistakes. It's going to make them seem more sensible, frankly, if not outright practical. Outside of Hearthstone, we're also going to be applying our probabilistic thinking to a great many other domains of life, even if we're typically going to be doing so unconsciously without thinking about numbers or percentages in any formal sort of way. And these are going to include matters like dating. Question, should I settle down with this person or should I keep looking for someone else? How likely is this relationship to succeed? You can apply this to career paths. What skills should I learn to help me secure the most income in the future? You can think about how to invest your money. Where will my investments get me the highest rate of return by the time I'm going to withdraw it? You can think about probability with the food you eat. Are these week-old leftovers still good to eat or have they spoiled? And just in other elements of daily life, like should I bring an umbrella with me today or not? And given the importance and prevalence of these probabilistic decisions, it's going to do us well to understand our own thinking about probability. So that's what the talk today is going to focus on. We're going to dip between some Hearthstone examples and some non-Hearthstone examples to help make these points. And while the Hearthstone examples might make the talk slightly less general purpose, it's going to perhaps make it a little more relatable to the people who are most likely to listen to it. So the first point we should touch on briefly is the term itself, probability. What does that word refer to? And this is going to be a case where the same word is often used to refer to different things, and that can confuse people. And in this case, there are two primary ways that we're going to be thinking about probability today. Two primary ways people tend to think about probability. The first of these concepts, the more formal type of probability, and what some people would argue is the correct understanding of probability, is to say that a probability concerns the frequency of an outcome occurring in a specified environment over a large number of repetitions. That is, you're asking how often does something happen in the long term? Now, it's important to specify here that ideas like a large number of repetitions and in the long term, these don't refer to any specific number of things, but rather the idea that you're going to effectively be repeating an action a nearly infinite number of times. And the more you repeat that thing, the closer the set of outcomes you observe should tend to get to an expected set of outcomes. So a simple example for this formal definition of probability would be our bag filled with marbles here. Let's say you have a bag that's filled with 100 marbles, and some of these marbles are black, and some of these marbles are white. You don't know how many of each are in the bag. So what you're going to do is you're going to close this bag up, you're going to shake it around, mix everything up, reach in there at random, and select a single marble. You're going to pull it out, record the color, put the marble back in the bag, close it up, shake it around, reach back in, pull another one out at random, record its color, and you're going to keep repeating this process over and over and over again. And you're going to be asking yourself, how many times did I get a white marble, and how many times did I get a black marble? And if you repeated this experiment, let's say 10,000 times, you found that 7,000 times you pulled a white marble out of the bag, you might say that you think out of the 100 marbles in this bag, 70 are probably white, 30 are probably black, and the probability of pulling a white marble is 70%. The probability of pulling a black marble is 30%. So in this sense, you can see that this first concept of probability refers to a series of events, or a frequency of events, over this specific context. How many times are you expected to draw a white or a black marble from this specific bag, given this specific sampling method over a long number of trials? How often do you see a black marble? How often do you see a white marble in the long term? The second concept of probability refers to individual beliefs about the outcome of a single uncertain event. So in this case, you might be asking people about whether they think it's going to rain tomorrow, whether you think a sports team is going to win a game against their opponent, or whether a particular candidate's going to win a political election. This is a more subjective sense of probability. So rather than talking about what happens in the long term, you're asking about some belief that concerns what's going to happen the next time, or during one particular event. And to return to our marble example, this more subjective sense of probability is referring to asking people about what they think the next marble you pull out of the bag is going to be. Will it be white or will it be black? And these two concepts are, of course, related. If you did that marble experiment 10,000 times and you observed a certain frequency of black and white marbles, you can use that information to make an informed guess about what you think is going to happen the next time you pull a marble out of the bag. But it's just important to note that these two concepts, probability as a long-term frequency on the one hand, and probability as degree of belief in a single outcome on the other, these are very, very different in terms of what they refer to. And in fact, they're so different that if you read some literature on probability, you'll see that there are a number of experts on the subject that have gone as far as to say that probability as a concept simply doesn't apply to a single trial event. Probability is only about long-term frequencies. That is, if there's a 70% chance that you pull out a white marble and a 30% chance of pulling a black one, it doesn't make sense to say that on your next pull you're going to pull 70% of a white marble, because you can't do that. It's either going to be white or it's going to be black. The two concepts are in this sense referring to very different things. And so you can kind of mentally understand this by saying the formal concept of probability, the one about long-term frequencies, this is about making a correct choice. And the more subjective single event probability is about getting a favorable outcome. And this distinction between making a right choice and getting a good outcome is notoriously difficult for people to grasp at times, but it does help to mean what it means. It helps to explain what it means to think probabilistically. So let's say I offer you a simple deal that you can see here. There are two spinners in front of you. Each of these is made up of 5 equally large sections. On one spinner on the left, 3 of those outcomes, the green ones, win you $1, and the 2 red outcomes say you don't get anything. The spinner on the right, 2 of these 5 say win $1, and 3 of the 5 say nothing. So what I'm going to do is I'm going to spin both of these. But before I do, you get to select one of the spinners, and you get the outcome from whatever it lands on. Which one of these 2 are you going to pick? Well, because obviously 3 chances are better than 2 chances out of 5. Pretty much everyone is going to pick the spinner on the left, and sensibly so. But this certainly doesn't mean that every time you spin these, every time you repeat this game, the one on the left is going to give you the reward and the one on the right won't. The first spinner is the smart choice to make, but only in the probabilistic long-term sense. There are going to be many instances where, strictly due to random chance, the more favorable spinner on the left isn't going to give you a reward, but the spinner on the right would have. Sometimes they may both provide you with a reward, and sometimes neither of them will. But because we don't know which spinner is going to be the correct choice on the next spin, we select the one that is going to be correct on the expected greatest number of spins in the long term. So, with these two concepts of probability in mind, understanding what the term itself actually refers to, I want to rewind a little bit and recap just some basic evolutionary theory to provide us with a deeper understanding of why probabilistic thinking matters so much. So at any given time, there are nearly an infinite number of possible actions available to living things, to you, to me, to everything. From the microscopic levels of internal cellular processes to the coordinated movement of the entire body across trillions of cells, there are pretty much an infinite number of things we might do at any given moment. And out of all those possible things we might do, a very, very, very small number of those things are actually going to end up being adaptive. That is likely to help you successfully replicate genetic material. As we put it in some of our early evolutionary psychology lessons, there are many more ways of being dead than there are of being alive, and there are many more ways to not successfully reproduce than there are ways of being successful at this. And of this already restrictive list of the possible adaptive behaviors you might take, there's an even smaller list of those that are maximally adaptive, whether in some average sense or given that specific situation. That is, it's not enough to just reproduce once and then you're done. You need to reproduce more than other members of your species, and the offspring you produce need to go on to continue to reproduce more than others if your genes are to remain represented moving forward. So across generations then, the process of evolution is going to act as a sieve or a strainer, like a pasta strainer, selecting for the variants that successfully pass through this process and pass on their genetic material most effectively. And this process of straining out the variants that are successful from the ones that don't naturally pushes organisms in the future towards certain paths of development and behaviors that have proven effective in the past. So out of all the infinite possible biological forms there might be, developmental pathways you might take, behaviors and cognitive systems you might have, only the very narrow band of them that successfully continue to reproduce remain in the world. In that sense, you can think of this entire process of evolution as a probabilistic one. Some behaviors and physical forms and developmental pathways are more likely to reproduce themselves than others, and given enough time and enough iterations, in the long term, the variants that are most likely to reproduce tend to become more represented in the overall population. Now that's the bigger picture importance of probability, but there's a more personal importance to probability as well. And you can phrase it this way. A persistent adaptive pressure faced by all living things, you, me, everything that's alive, is that the future is unknown. Even though the future may well be determined by the physical laws of our reality, our ability to know that future is severely limited. We don't know for sure whether this object we're going to put in our mouth is food or poison. We don't know which potential mate is fertile or infertile. We don't know which paths in the world will lead to food or water or predators. We don't know which people in our environment are going to be good social investments and which ones won't. Since the future is unknown, and there's nearly an infinite number of possible things you might do, and only a small number of that infinite possible things would be wise to do, living things need a way to narrow down these possibilities and select the useful courses of action from the less useful ones. And so what living things seem to do when they're confronted with this uncertainty about the future in practice is to use the available information from our immediate environment and make an informed guess. And these informed guesses are probabilistic thinking. We engage in it constantly and unconsciously. We're always taking in cues from the environment, the immediate environment, what we call the proximate environment that we find ourselves in. We assess which of these cues were historically associated with certain adaptive outcomes, and use those cues to inform our behavior in the moment in an effort to predict which things are going to be useful to do next. Now, sometimes these guesses are going to be correct. So in this case, you guess correctly that the object in the world that's reflecting light into your eyes is a reproductively viable mate interested in having sex with us, and the net result of that is going to be a healthy child that goes on to reproduce itself, and as such, becoming aroused is the appropriate adaptive response. So we're receiving some environment from some input from our environment, specifically in this case some wavelengths of visible light, and the specific pattern of those happened to be associated with reproductive opportunities in the long run of our species' evolutionary history, and so this input of light can guide our behavior in the short term to become physically aroused, psychologically motivated, and the whole body can coordinate its movement to approach the reproductive opportunity and engage with that instead of doing what else it might do. Now, other times, the objects that are sending these similar visual signals into our brain, that is, they may resemble a reproductively viable mate, but that signal doesn't actually correspond with what the part of our mind that's making the guess thinks it does. That is, what looks like a reproductively viable mate might be infertile. It might be a member of the wrong sex. It might be a member of the wrong species. It might be an inanimate object in the case of a doll or a mannequin, or even simply the glowing screen of a monitor in the case of pornography. So in these cases, our bodies may still generate arousal because they're receiving an input that tended to be associated with reproductive opportunities in the past, but it makes an incorrect guess in the moment as to what the adaptive course of behavior would be. So if your threshold for becoming aroused is too broad, you get aroused inappropriately by too many things too often, you're going to make a lot of bad guesses about what to do, and you're not going to reproduce as well as you could have. By contrast, if your threshold for getting aroused is too restrictive, you're only aroused under very specific circumstances here, you might make bad guesses and miss out on opportunities you otherwise could take that would have been adaptive in that moment. And so the process of evolution helps hone the guesses of our mind down to their most useful avenues. And these examples help us better appreciate this probabilistic nature of the evolutionary process and let us see the importance of both of these different conceptualizations of probability. As far as living things are concerned, the future is uncertain because we lack the information and tools to know it. Because we can't know the future, living things make guesses, consciously and usually unconsciously, about what the most adaptive course of action will be in their current situation. The more accurate those guesses tend to be, the more likely they tend to reproduce, and over time this results in organisms that possess better tools for processing this information and making those guesses, assuming the environment remains constant. If the environment is going to remain constant, the organisms will become better adapted to their environment because they're better at making guesses about what's going to happen next and tailoring their behavior and physical forms accordingly. But sometimes environments can shift, and what was previously a good guess now turns into a bad one, and the course of evolutionary pressures shift. For example, there didn't used to be pornography or hormonal birth control, but now there are. And the presence of these things can make previously adaptive responses to certain patterns of information now into maladaptive ones. What was a good decision can now become a bad one. And importantly here, we can see that you can have a cognitive mechanism in your head that can make the correct choice on average about what to, say, get aroused to, but it's not going to make the correct choice every single time. So behavior that is appropriate on average is sometimes inappropriate in the moment. Difference between making a good decision and getting a good outcome. You can make the right choice probabilistically in terms of the long-term human evolutionary history, but still get a bad outcome in the short term, in this specific instance. Now, what makes discussions of probability tricky is how tied together these two different concepts of probability are to each other. People do not think about probability often in this long-term sense, and that is because probability is, or rather life, is not a series of long-term problems. Life is a series of short-term problems. To put this in what might be confusing terms, you're not going to be flipping a coin 10 times as much as you're going to be flipping a coin once 10 different times. And as it turns out, there's a pretty big difference between these two framings when it comes to understanding how they impact your psychology and your behavior. A first example of this comes from some research reported by a man named Clifford Conold in 1989, paper entitled Informal Conceptions of Probability. And this research involved grabbing 16 undergraduates, nice sample of convenience, college kids, and posing them with questions related to probability and just recording how the students thought about these problems. That is, you're asked to think out loud about this probabilistic situation you're presented with, and do your best to verbalize what your internal thought process is and what conclusion you reach. Now, in one of those questions, the students were asked about a weather prediction problem. That is, you're told that there's a weather forecaster who says there's a 70% chance of rain tomorrow, and then tomorrow comes and it doesn't rain. The students are asked, what would you conclude about the statement that this forecaster made? And And then after this, they were then told to imagine that on 10 of the days that the forecaster predicted a 70% chance of rain, it didn't rain on 3 of those 10. So it did rain on 7 of those 10. The students were also asked what they would conclude about the accuracy of the forecaster in that second case. So, taking these in order, when the 16 students were first asked about the forecast of a 70% chance of rain for tomorrow, when it didn't rain, 6 of those students said that the prediction was wrong. They thought the forecaster had made a mistake. And when you examined their reasoning, what the students appeared to be doing was something along the lines of thinking that a 50% prediction was effectively a guess. As if the weatherman was saying there are 2 possible outcomes: it's going to rain or it's not going to rain. I have no idea what's going to happen, so I'm just going to pick one of these 2. And since a 70% chance was higher than a 50% chance, the students took this to mean as the weatherman was saying closer to something along the lines of, I believe it will rain tomorrow. So these students were taking a probabilistic statement about a frequency, and they were transforming it into a prediction about a single event. Again, here, since it can either rain or it cannot rain, the students seem to interpret the weatherman as saying that a 70% chance is going to rain tomorrow. A 50% chance would be a guess. Anything below would be transformed into it won't rain. Anything above 50% transformed into it will rain. Now, not all the students did that, of course. Other students did say that they thought if it didn't rain tomorrow, that didn't exactly mean the forecaster was wrong, because there was still a 3 in 10 chance that it wouldn't have rained. So some of these students were thinking about probabilistic problems like this in the long term, and some were thinking about it in the short term. But things get quite a bit stranger with respect to the second question. So this is when they're told the forecaster said on these 10 days, there's a 70% chance of rain. And on those 10 days, on 3 of them, it did not rain. What would you conclude about the predictions? In this case, 9 of the 16 students suggested the forecaster could have improved their prediction skills, and another 4 expressed some conflict over whether the forecaster had been perfectly accurate or not. So that's to say, when the students heard the weatherman forecasted a 70% chance of rain on these days, and it rained on 70% of those days, many of the students believed the forecast was, to some extent, inaccurate. Only 3 of the 16 students actually said the forecast had been perfectly accurate. So when it came to probabilistic thinking then, some of the students were, at some of the times, thinking about this as a single short-term prediction. Will it rain tomorrow or will it not? And other students were thinking about it more as a frequency of repeated long-term events. And they would also sometimes just flip between these two in their own thinking over time. Now, at first, it might seem pretty strange to hear the results phrased this way. Because if the weatherman's forecasting a 70% chance of rain on 10 days, and it rains on 70% of the days, boy, that sure seems perfectly accurate, doesn't it? But many students were saying it wasn't. So how can we understand their reactions here? Now, many people, including many researchers on this subject, it seems, would be inclined to suggest that the students were wrong, or that the students lacked the cognitive abilities to think about probability correctly, or basically that they were stupid. And in my view, I'd say that the responses of these students aren't necessarily wrong or irrational, but you need to place them in the correct framework to really understand it. Specifically, the answers that the students are giving seemed to reflect the fact that living things are not interested in acquiring knowledge without context or value. We don't think about probability just because, for the same reason you probably don't go outside and count the number of blades of grass on your lawn just because. All the value of this information depends on what you're going to do with it when it comes to guiding your behavior. I understand that might be a little bit abstract, so to understand this point, I want to look at another example from the same paper. The students were presented with a standard 6-sided die. 5 of these sides are black, 1 of these sides is white. And they were asked, if I roll this dice 6 times, what's the most likely outcome? That I'm going to get 5 black and 1 white, or that I'm going to get 6 black? Now the answer here is that on each of these 6 rolls, we should expect to get white once on average. That is indeed the most likely of the long-term expected outcomes. If 5 sides are black and 1 is white, we're more likely to see 5 black rolls and 1 white roll for every 6 than 6 black ones. Despite that, there were some students who, when they were presented with this question, said that 6 black rolls were actually more likely than 5 black and 1 white. Now, why would they conclude that? To be clear, they are getting the answer wrong in the long-term sense of probability. But that's because I think they're actually answering a different, much more practical question about short-term probabilities. And I think you can all understand the position of these students who said that 6 black is more likely to happen if I present you with, again, a very simple situation like our spinners before. I have this die that has 5 black sides and 1 white side. I'm going to roll it 6 times. If you can correctly predict what the color is going to be the next time I roll it, I will give you $1 every time you're right. So I'm going to roll the die. You make a prediction, I roll the die. You make a prediction, I roll the die. We repeat this 6 times. What is your best guess? Well, in this case, the correct guess would be to always guess black is going to come up next. It doesn't matter if you roll that die once. It doesn't matter if you roll it 1,000,000 times. Even though you might know that the most common outcome every 6 rolls is 5 black and 1 white, this is what the long-term result is going to be. In the short term, your guess will never vary off of black on any single trial if you want to make money. And I think this is probably the way the students were interpreting this question, when they said that 6 black rolls are going to be the more common ones. Because even if, again, you're rolling the die 1,000,000 times, predicting white will show up on the next roll is something you should never do if you want to maximize the number of right answers you have. No matter how aware you might be that white is likely to show up occasionally, at some point, you simply can't predict when it will, and so your best guess is never to say white. It's always to say black. You will simply pretend the white side of the die doesn't exist for all practical purposes. And this really highlights the point that information about long-term frequencies is pointless information if you can't use it to guide your behavior in single-instant short-term events that life is made up of and we are repeatedly faced with. And indeed, we can use that same logic to understand this weather prediction problem. If I tell you there's a 70% chance of rain tomorrow, this information means something very different in the sense of a long-term frequency versus what you're going to do tomorrow. If there's a 70% chance of rain, you either bring an umbrella on your trip or you leave it at home. You can't 70% bring an umbrella and 30% not bring one. You may know that it's only going to rain on 7 of these 10 days, but you can't predict which of these days are going to be the rain ones and which of them won't be. So for all practical purposes, what we have to do is convert this abstract long-term probability into a dichotomous action. You either bring an umbrella tomorrow because yes, it's going to rain, or you leave the umbrella at home because no, it's not going to rain. And people care about this because there are consequences for what you do. If you bring an umbrella, it's going to take up space, it has weight, you need to keep an eye on it, remember to bring it home, make sure you don't lose it, make sure it doesn't get damaged. You would rather not bring the umbrella if you didn't have to, because it's just going to get in the way of your day. But if you don't bring that umbrella and it does rain, you get wet, your possessions might get damaged, you might end up having a pretty miserable time. So unless this information provided by the weatherman can be used to make a better informed choice in the moment, in the short term, it is simply useless, contextless information. And people, indeed all living things, don't do well to waste their time attending to pointless, useless, contextless information. So in the abstract conceptual sense, some of the students in these experiments might be misunderstanding what probability refers to formally. They might say the weatherman is wrong if he said there's a 70% chance of it raining and it doesn't rain. They might say it's more likely that black is going to come up 6 times out of 6 rolls instead of 5 black and 1 white. And we can chuckle to ourselves about how bad they might be at misunderstanding probability, but what they're doing might actually be far more practical. That there's a very vital difference here between providing a correct abstract answer and actually doing something useful with the information you're presented with. Now, on this point of needing to do useful things with the information, people can, at times, disregard the role of random chance factors in determining outcomes. Now, random chance doesn't need to refer to anything that is strictly speaking random, but rather referring to this idea that there are multiple forces impacting an outcome that we're simply unaware of. We can't predict it. So when you roll, let's say, some dice, the laws of physics should allow you to predict exactly what side they're going to land on. But since we lack that complete information, we just say that factors like chance or luck determined the roll. That's what we mean when we say it. So when you hear the word chance, just mentally try and replace that with thinking about unpredictable or unknown factors that determine an outcome. And as we just mentioned, people ignore the role of chance factors somewhat regularly, if not very regularly. We get enamored by stories of celebrities who worked hard and really grinded at their craft to reach the peak of stardom, some famous actor or musician. But we often don't think about all the other talented, hardworking people that just never had their career take off because they weren't in the right place at the right time. And you might see a post about a Hearthstone deck that hit rank 1 legend and attribute that rank to the power of the deck without being aware of all the other people who played the same deck without anything approaching that level of success. In fact, that's why the channel here has the command for exclamation point win rate, which takes you to what you're seeing on the screen right now. On the left-hand side, the win rate column, this was my win rate percentage on each day of the month. The games column to the right of it, that's how many games I played to get this win rate. And on the right side, you see some aggregated data. So this deck had an average win rate of about 53%, but there are some days where I'm winning 30%, and there are some days where I'm winning 70%. Now, if you imagined each of these rows was a different player, so the first player plays the deck 48 games, has a 50% win rate. The next player plays the game 36 games, has a 44% win rate. One of these players has a 70% win rate over 44 games. One of them has a 32% win rate over about 30 games. If you imagine these were all different players, you'd probably understand if they all came away with a very different perception about how good this deck is. Some would conclude the deck is amazing because they won 70% of their games, and some would conclude the deck is terrible because they won only 30% of their games. But in this case, it's the same deck, it's the same player, me in this instance, and it's the same meta that it's being played in. And the results can vary dramatically from day to day, just due to simple chance factors. Very few people, by the way, would conclude that these chance factors are what's determining their win rate. In another Hearthstone example, you can see this in my guide, exclamation point guide. This is one of our new examples. There are 2 priest decks, one on the left side, one on the far right side. These 2 decks differ by a single card choice. The list on the left plays 2 copies of Deafen, the list on the right plays 1 copy of Deafen and 1 Aman'Thul. They're both played for about 250 games apiece, and their win rate differs by almost 10% exactly. Now, this is almost certainly due to random chance factors and not a reflection on how switching a single card in the deck increases or decreases your win rate by 10%. But you'd have a very hard time convincing many people about that, especially because 250 games sure seems like a large amount of games. It seems like you should be able to discount the role of chance over 250 games. But apparently, not so easy to do. And indeed, if you remember our early example of these 2 spinners here, one with 3 out of 5 favorable outcomes, the other one with 2, This was actually a game that was designed by a researcher called Ruma Falk to help assess children's abilities to compare probability. Because you can't exactly ask children to verbalize a complex internal thought process, you give them some simple games like this. And they were talking about this example in a 1992 paper. It's called The Psychology of Learning Probability. This game was actually criticized by parents, and it was criticized by some educators for being an uneducational game. The critics were apparently uncomfortable with the idea that the children might not get rewarded for selecting the correct option, or they might get rewarded for selecting the incorrect option. Now, the whole purpose of this game was to teach children about the role of chance and what probabilistic outcomes are. And ironically, the critics wanted to remove this element of chance to avoid teaching the children what they thought was wrong. They thought if the children picked the one on the left, they should always get rewarded because they made a right choice. Ironically, this would teach children that chance factors didn't exist. It would teach them something incorrect. Now, interestingly, what they found is when children were playing these games, many appeared to overstate their probability of winning. The children they basically do what the Weatherman problem did before. They would say probabilities that are above 50% are viewed as sure to win. They would say something like, if they pick the left spinner, now I'm sure to win. Whereas if they pick the spinner on the right, they might say, now I'm sure to lose. They were converting a probabilistic outcome into a certain one mentally. And this tendency doesn't just exist in children. And it can be seen in how people react in Hearthstone to, let's say, losing a favorable matchup. For example, how am I losing this matchup? It should be free for me. You might see when they queue into an unfavorable match, or when they know they're going second, and because of this they're unfavored, you might hear people say, well, I guess we're playing against the Warriors, so now I'm guaranteed to lose. Or, oh, I went second, so I lost. It's not uncommon to see people responding to such situations with an amplified negative emotion owing to their expectations about what they're predicting is about to happen on the next trial. So they use information about what's likely to happen in the long term. You're more likely to lose going second, to predict what's going to happen next time with relative certainty. I'm going second, therefore I'm going to lose. And they disregard the role of chance. And we can also see this in the context of Hearthstone players responding to, let's say, relatively small numbers of games, like what you see here. Even adults are prone to observe a deck win 8 out of its 10 games, or 70 out of 100 games, whatever it is, and think that this deck is powerful and that such success is likely to replicate consistently into the future, even if such win rates are almost never observed in substantially large samples over the entire history of Hearthstone. So it's very easy for someone to win a lot in a small number of games by chance factors, but completely disregard the role of chance and attribute that performance to themselves being skillful, to the deck being powerful, or something else. Indeed, as Falk puts it in the paper, people typically regard a long run of outcomes that turn up strictly because of chance factors as non-random occurrences. Thus, when you observe a sequence of hits or misses in a basketball game, or wins and losses in a Hearthstone game, they attribute that random run, which seems too long to be the product of chance, to some mysterious non-random agent. So in some cases, let's say like you flip a coin, it comes up heads 15 times in a row. You may come to believe that the coin is fixed. You may also come to believe that the coin is very likely to come up tails on the next flip, because coins come up heads and tails 50% of the time, and this coin is lagging behind because there have been a bunch of heads that it flipped before, so it's more likely to come up tails in the future. We attribute this to some non-random factor about the coin, even if it is just totally normal to occasionally see a coin come up heads 15 times in a row. And we can also, of course, think about this in Hearthstone where people talk about, let's say, a rigged matchmaking system, where people start to attribute random losses, strictly due to chance factors, to some intentional agent that is messing with them and causing them harm. So at times, people seem to ignore the role of chance in predicting and producing an outcome. At first, that may sound strange, because we know, if you sit down and ask everyone, we know that unpredictable chance factors matter. We know that they happen regularly. And yet we often seem to repeatedly ignore them. Why do we do this? Now, in my view, ignoring the role of chance factors can actually make a lot of sense, because frankly, there's not much we can do about it. First, by their very nature, a chance factor is an unpredictable one. And if you can't predict it, attempting to incorporate this into your predictions about the future would be pointless. In such cases, it's relatively easy to disregard chance factors simply because chance isn't observable and chance isn't actionable. Maybe that priest deck that we saw before, maybe the difference in those two priest decks across 200 games each was largely due to chance. Hell, maybe the performance of a deck across 40,000 games is actually still due to chance. Maybe it's less likely in the 40,000 case, but it's still possible. Maybe chance produced those outcomes in both cases. But what can we do with that information? The answer doesn't seem to be very much. And if we can't do much with that information, why are we going to waste time thinking about it? However, the disregarding of chance factors may ironically also be the correct way to make decisions in the long term. Think about it this way. If you watch someone win with a deck 10 times in a row, there is, of course, a certain chance that this outcome was just due to good luck, and that player or that deck isn't particularly likely to win in the future. However, there's also a chance that this person is really good at playing the game, or the deck they're playing is really powerful. And when you compare the relative probability of these two hypotheses, are they lucky or are they good, in the moment, given the information you have, it sure seems much more likely that the person is skilled or the deck is powerful than that they simply got lucky 10 times in a row. While the chance explanation for the result didn't get disproven by any means, at the moment, the weight of the evidence does seem to point in the direction that maybe the deck actually is that good. Now, of course, what you could do is test this hypothesis by observing the performance of the deck in the future. Have this person continue to play it. But this is where we run into the practical problem of how many times do you need to watch someone do something before you make a conclusion from it. Because there are an infinite number of things we might do in our life, there are also an infinite number of competing possible demands on our time. And we can't just sit around and watch someone play 10,000 games of Hearthstone or flip a coin 10,000 times in a row. More information might be useful to us in making a decision and minimizing the role of chance in determining the results, but there simply aren't enough hours in the day to collect this information. And that would just be if you wanted to answer a single question about, is this Hearthstone deck good? Now try to apply this method of repeating things 10,000 times to everything that happens to you in your life. You're going to quickly realize how impractical it is to try and assess everything in the long term, most especially things that can't be repeated the way flipping a coin can. Let's say you want to raise a child or get into a relationship. You can't rewind the clock on this and do the same thing 10,000 times in a row. Yeah, maybe chance factors are going to affect the outcome, but what can you do about it? So even though this decision to disregard the role of chance in determining outcomes might not lead to the correct decision in that moment, it might ironically yield the largest number of correct decisions in the long term of your life, given the practical constraints on our time. Your guesses may not be perfect if they disregard chance, but they may also represent the most efficient uses of your time and the best available information you have. Remember here, the outcome of evolution isn't maximizing the number of times that you're right about something. It's maximizing the number of times you do something useful. Sometimes you need to do things that carry short-term costs occasionally for the greatest long-term gains, and ignoring the role of chance can be one of those things. Now, on the subject of disregarding chance factors, let's also think a bit about how you're collecting information and how that might affect your beliefs about probability. Let's return to our big marble bag example here. Imagine you have a truly massive bag of marbles. There are 10,000 marbles in this bag. You can't sample marbles from this bag in any practical way. It's too big. You can't shake it up and mix it around. You can't grab something at random. It's not something feasibly you can do. So what you do instead is you get a small bag and you scoop, let's say, 5 handfuls of marbles into your bag. And then, since you can work with this one, you shake it up and you sample randomly from it. So rather than sampling from the entire population of marbles at random, you're selecting a subsample that you can more easily work with. So let's say in your bag, you come to believe that there's a 70-30 split between black and white marbles because that's actually what your bag contains. However, if the subsample of marbles that you have, for chance reasons, just happens to contain a 70-30 split, whereas the larger bag contained a 50-50 split, your particular feelings about the probability in the larger bag will be wrong. But it's not because you're biased in any way, and it's not because your method of collecting information is mistaken. You simply had a non-representative sample to work with. And there are practical parallels to this, which we should all be familiar with. And one of these is the well-known phenomenon of the echo chamber. So if you find yourself constantly surrounded by people who all think the same way that you do, they all agree about the same things, the mistakes in your thinking become harder to spot because you are rarely, if ever, exposed to contradictory evidence or lines of thought. If you are repeatedly exposed to the same non-representative sample of information about the world, you may come to believe things which aren't true, even if you yourself have no personal biases. You might be an unbiased observer who is simply exposed to biased information, and because of this, you are going to rationally develop a biased conclusion. You will correctly develop an incorrect conclusion simply because you're being exposed to the wrong information by chance. And sometimes, people can even perceive the role of chance factors in the world strategically. That is, sometimes people don't ignore chance, but they actively downplay the role of chance or inflate the role of chance in very self-serving ways. This is a very fancy way of saying sometimes people are biased. And anyone who's heard enough people talk about their experiences and conclusions from playing Hearthstone, or indeed any other games for that matter, will be familiar enough with this point. If you find yourself on a losing streak and you're unable to rank up, you see people start to complain bitterly about how there's no skill component in Hearthstone and the outcomes are based entirely on luck, or matchmaking is rigged, or something shouldn't exist because it's not good for the game. And in a non-gaming example, you may hear someone complain about their lack of success in life being due to the shifting standards of society and culture around them, or because they're born into poverty, or they experienced some setback that stopped them from getting their big break, like some promising high school athlete that just suffers a major injury. What all of these ideas share at their core is the premise that says this: I would have been successful if not for that chance factor. And you can fill in the blank with whatever that chance factor is. I would have won that game if it wasn't for that random roll. I would have gone pro if I didn't blow out my knee during practice. I would have been successful if only I was born into a more affluent family. Now, this isn't to say that these claims are necessarily wrong. To be clear, some of them are. The claim like Hearthstone has no skill to it, very clearly wrong, very clearly disprovable. And some of them have some truth to them, like it is more likely to be successful in life if you are born into affluence instead of into poverty. But the important point to bear in mind here is that the truth of these statements is not their primary function. The goal of the statements is not truth. The goal of the statement is persuasion. And when you look at what people say and think about probability sometimes, it's a lot less about making an accurate statement and more about making themselves look good socially. So if you think about Hearthstone or video games in general, it might seem really weird that people get so worked up over winning or losing them. It's just a game. It was just a bad roll. Shit happens. What are you going to do? Why are you getting so worked up about this? But a deeper analysis of these logics and emotions help make things a little bit more understandable, a little clearer. In brief, we all possess some stable but invisible characteristics. Things like intelligence, creativity, kindness. These features, what we might consider our personality, our skills, our talents, our potential, they do have predictable long-term impact on how we are going to behave, what we're going to achieve, and accordingly, how valuable of a social asset we are to other people. We would all rather have a competent friend to an incompetent one. We would rather have a kind partner to a hostile partner. We want to have someone who's going to, in the long term, be likely to deliver us positive outcomes instead of negative ones. And these traits that we have are a very important factor in determining if it's going to work. But since we can't just look at someone and assess these traits directly, people have to do things that credibly signal them to others. I have to be able to do something to show that I possess these traits that other people can't do because they don't possess these traits. The behavior, in other words, needs to be hard to fake. So, in a simple example here, it's very easy for me to say, I am rich. I possess a lot of money and resources. Easy for me to say this. It's much harder for me to have a genuine Rolex watch on my arm and get into my Lamborghini. It's easy for anyone to say that they're kind, but it's harder to give up your time and your energy to go help others in a demonstrable way. And for the sake of our gaming example, it's easy for anyone to say they're smart and creative, but it's hard to win games of Hearthstone against real opponents with decks that you came up with yourself. So as such, if you're failing to perform in a video game, or failing to perform in life, that may be taken by others as a credible, honest, believable signal that you really do lack the traits required for success and, in the long run, are likely to continue to fail. If that's the case, they may be less inclined to be interested in pursuing you for social relationships or romantic relationships, and they would rather spend their time invested in other people who are more likely to deliver them positive results. If, however, you can persuade others that you failed because of chance, luck-based factors, that would mean that your poor performance shouldn't be attributed to some stable internal part of your personality that's likely to replicate. That is, I'm going to be a better social investment. Just because I messed up before, that's not going to keep happening in the future. I got unlucky. I wasn't late because I was selfish or I was forgetful or I don't value your time. I was late because I got stuck in traffic. And anyone can get stuck in traffic no matter what their intentions are. I just got unlucky. So don't take my being late as a sign that something is wrong and likely to be bad in the future. Conversely, you might have, let's say, a successful businessman downplay the role of their parents' wealth in determining their own success. They might say something like, my dad gave me a small loan of $1 million. The Hearthstone player that finds success with their off-meta homebrew deck might post about their 70% win rate over 50 games along with a guide to let everyone know that their deck is good and they're really creative and they're really smart and it wasn't due to chance at all. Their successes, you see, weren't due to good fortunes. It was all due to these stable internal traits that are definitely going to predict the future performance. So you should listen to me, you should hold me in high regard, you should do what I say because I've been successful. So in such cases where persuasion and people's self-interest is at stake, we should expect attempts to manipulate the perceptions of chance in other people's minds. If you perform poorly, it's probably in your interests to get others to believe that this was just a one-time thing and it wasn't even your fault. And if you perform well, it might be in your interest to persuade people that this is a long-term thing that's likely to happen again. Everything you touch turns to gold. You're a genius. You're the best. But in both cases, the truth of the matter is secondary, and the primary purpose is persuasion. So, let's shift gears a little bit now to another somewhat broad, but very, very important point to bear in mind when it comes to thinking about probability. And this is that our cognitive systems, our brain, requires specific inputs if we want it to operate properly. If you want to use probability better in your own life and reach more accurate conclusions, you need to ensure that you're giving your mind the information it needs in the format that it needs it if you want it to work. To use a very simple example here, our eyes can only take in a very specific wavelength of the electromagnetic spectrum that you see here. This very narrow band that we call visible light is what we are capable of seeing, and it's a fairly small slice of this spectrum. We are literally blind to electromagnetic waves with lower frequency, lower wavelengths. Things like infrared light, things like microwaves, we can't see those. We also can't see things with higher wavelengths, like ultraviolet light or X-rays. If you are providing your eyes with infrared light predominantly, they're not going to work very well because it's not the type of information they're made to process. In more mundane terms, maybe you might say that a can opener is made to open cans, and a can opener is not made to open bottles. If you're trying to use a can opener to open a bottle, you're not going to get very far. Same thing's going to happen with our mind and probability. So in order for our cognitive systems that think about this stuff to operate properly, they require specific kinds of inputs. And as it turns out, a lot of the language that we actually use concerning probability in the modern world and in psychology experiments doesn't actually work particularly well. Our minds simply don't grasp this representation of information. And think about it this way here. I give you a calculator. You have a calculator on your phone. Everyone has access to this stuff. And I want you to use this calculator to calculate 1 plus 2. We can all do that if we use the standard numeric system that we're familiar with. By contrast, if I tell you, get your calculator out, I want you to add 1 plus 2, but you need to represent these numbers in Roman numerals or binary, your calculator is not going to give you the right answer because you put information into it in a form it can't process. If you're curious, by the way, binary is a language made up of only ones and zeros. So if you want to add 1 plus 2 on a calculator in binary, 1 is still 1. So you type 1 into your calculator plus, and then to represent 2, that's 2 zeros. So you would go 1 plus 0, 0 equals, and that's going to tell you 1. Because the calculator isn't expecting binary. The correct answer is 3, but you get the wrong answer because you're feeding it information to the calculator in a form it's not expecting to process. So what kind of information formatting is our mind expecting? One of my favorite researchers in general, his name is Georg Gigernezer, very hard to pronounce there. He talks about this in a 1994 paper entitled Why the Distinction Between Single Event Probabilities and Frequencies is Important for Psychology and Vice Versa. Actually, a book chapter, but don't worry about that. As he argues, if you want to try to imagine what human life was like for hundreds of thousands of years over our evolutionary history, there's been no concept of advanced mathematics. There wasn't anything in the way of literacy, even. We have an illiterate, innumerate world. We don't have letters, we don't have numbers, we don't have reading. People don't think about these things naturally in terms of advanced concepts like percentages and statistics. What the human mind has access to in this world is what he calls a natural frequency. You can think of a natural frequency along the lines of saying, 3 of the last people I have encountered have been kind to me, rather than something more abstract, like 30% of these people have been friendly. Now, at first, this might seem like a minor difference. 3 out of 10 people have been friendly versus 30% have been friendly. Because, after all, these are the same things. 3 out of 10 is 30%. But like our calculator example, trying to put binary into it, there's a big difference to our brains in terms of how you represent this information. And we're going to run through some examples to show you that, make it a little more clear. First of these, this is an experimental example used in the probability literature known as the Linda problem. In this example, you read this description about a woman that goes as follows. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which of the following is more likely? Do you think that Linda is more likely to be a bank teller, or that Linda is more likely to be a bank teller who was active in the feminist movement? When faced with this question, the vast majority of people say that it's more likely that Linda is a bank teller who is more active in the feminist movement than that she's just a bank teller. Indeed, depending on the study you're looking at, about 8 or 9 out of every 10 people you survey is likely to give answer number 2. But that answer is wrong. By definition, that answer must be wrong. Because in case 1 and 2, Linda is a bank teller. So in the first case, you're asking, is it more likely that she's a bank teller? In the second case, you're asking, is it more likely she's a bank teller and also something else? And if you break this down into very, very abstract language, you're basically asking, like the Linda problem itself, the description doesn't matter. You're asking, what's more likely? Is Linda X or is Linda X and Y? It doesn't matter what the description is. The answer is always X. So in such cases, because most people are getting this answer wrong, a lot of researchers concluded that the human mind is really bad at thinking about probabilities. It simply doesn't possess the capacity to do it. It doesn't have the right tools to even process this information. However, it seems that the results from that Linda problem are actually largely due to how the researchers are posing the question. They seem to be posing it in a way that the human mind isn't prepared to deal with. As Gerd points out here, you can keep everything about this example the same, but you make one small change to how the question is asked, and it makes all the difference in the world in terms of what answers you get. So now we modify the Linda problem. We give people the same description as before. Linda is 31 years old. She is single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. And then they ask this question instead. There are 100 people who fit this description. How many of them are bank tellers, and how many of them are bank tellers and active in the feminist movement? Once this question concerns natural frequencies, how many people out of 100, the number of participants that make this error falls dramatically. It goes from 80 or 90% of people getting the wrong answer to about 10 or 20%. Everything about the example is otherwise kept the same. But now people are saying it's much more likely that these Lindas are bank tellers than they're bank tellers who are also active in the feminist movement. Simply by changing the way you ask the question, the number of correct answers we get spikes up massively. Let's consider another example of how the representation of this information matters. This is another classic question that's asked to people researching probability. Imagine you're a doctor and you're trying to screen people for a disease. You know that about 1% of the population has the disease, but you don't know who. You have a device that can detect the presence of the disease, but it does so imperfectly. If someone has the disease, there's a 90% chance the device will say they have it. If someone doesn't have the disease, there's still a 1% chance that the device will say they have it. The device has reported that Mr. Smith is positive. What is the probability, what is the chance he has the disease? In such studies, where participants are asked this question, almost everyone provides the wrong answer. Many people provide an estimate, it's about 85% likely that Mr. Smith tests positive. The reality is the chance is much closer to 50%. It's close to 1 in 2. And this incorrect answer that people give isn't just relegated to undergraduates or random people. When they did this exact same problem with 100 physicians, doctors, who were asked the same question, almost every single one of them got it wrong too. This isn't simply a matter of education or intelligence that causes people to get the wrong answer. So let's imagine we ask the same question again, but we present this information differently. We say this. Imagine you're a doctor and you're trying to screen people for a disease. You know that 1 out of every 100 people in the population has the disease, but you don't know who. You have a device that can detect the presence of the disease, but it does so imperfectly. You give the test to 100 people. If you give the test to 100 people, the person who has the disease will almost always test positive. Of the 99 people who don't have the disease, we should also expect 1 of them to test positive as well. If you give the test to 100 people and it says Mr. Smith is positive, what is the chance Mr. Smith has the disease? In this case, the information is almost identical, but instead of representing it as percents, you are representing it as a natural frequency. And now people have a much easier time answering this question. Well, if you give a test to 100 people, 1 of them is going to test positive for the disease, and 1 of them is going to test positive and not have it. So 2 people tested positive, 1 of them probably has it, 1 of them probably doesn't. The answer is 1 and 2. So even though the information in the problem is the same, people's answers get radically different, and now almost everyone starts getting this question right. Our minds are expecting the information to be presented in a certain way. We don't do well with percentages. Percentages are these weird abstract concepts that have nothing to do with our evolutionary history. This is much more akin to what we're used to, and accordingly, we get the answer right much more often. So a real takeaway from these studies here is that when you're thinking about probabilities, say when you're looking at Hearthstone data here, you need to sometimes mentally reframe this information in your mind to more easily understand it. So let's sum up a lot of what we reviewed today into a single example. Let's say you're browsing around the Hearthstone data sites and you see that a deck has a 53% expected win rate, and further, it is the highest win rate among all decks in the game. You will probably feel pretty good about queuing that deck up. You'll be expecting success. After all, 53% is above average. So you're more likely to win than you are to lose. And since this is the best deck in the game, you know you're making a smart choice by queuing it up. When you do this, your mind is going to start making predictions about what is going to happen in your next game. And every time it's making that prediction, based off the available information it has, the right prediction to make is, I'm going to win. I'm more likely to win than I am to lose. I am playing the best deck in the game. Therefore, I am likely to win. If I have to predict win or loss, I'm going to predict win every single time. And knowing nothing else, that is the single best prediction you could make in the long term for the largest number of accurate predictions. But this will not mean you are accurate every time. In fact, you're going to be wrong a lot of the time. And those times you are wrong is going to make you feel a bit crazier than usual and have a worse time than you need to. After all, you're playing the best deck in the game. You're supposed to be winning, and you just lost 4 games in a row. How could this happen? You were favored. You made the right choices. You were supposed to win. You're mentally transforming this I am favored into a prediction of, in the next game I'm going to win, without even thinking about it. And these thoughts are so easily capable of poisoning your enjoyment of the game in the short term. And there are a lot of short terms. In fact, as we're concerned, when we're playing Hearthstone, there are almost exclusively short terms. Every turn is a short term. Every game you queue up is a short term. Every day is a short term. Maybe if you play a lot of Hearthstone, you could start thinking about a full month worth of results as being a long term, maybe. But even to get to this point of looking at a single month worth of data, you have to go through dozens or hundreds or thousands of individual short terms. In every one of those short terms, your mind is going to be making those predictions. We live our lives in these short terms, moment to moment, so we have to rephrase our expectations. You are picking a deck that's expected to win 53 out of every 100 games you play, which means you're expected to lose 47 out of every 100 games you play. And that is assuming you are as good as your opponent and the field you're playing against is relatively constant. And further, not every 100 games you play is going to be perfectly representative of that long-term win rate. Sometimes in 100 games, you're going to have substantially higher win rates, and sometimes in 100 games, you're going to have substantially lower win rates. So if you queue up to play Hearthstone and you're only playing 5, 10, 20 games a day, we should not be expecting our short-term results are going to match the long-term with any consistency. If you've set this expectation that it will, you're going to have a bad time. And finding some way to adjust that expectation is a great way to find more enjoyment in playing your games of Hearthstone. Another takeaway here is that when you're presented with these types of abstract numbers, like 53% win rate, you're not acquiring this in the way that you're going to acquire a natural frequency. We can see that in the example highlighted previously in the exclamation point win rate command. It's much different to see an average win rate presented as a single number than it is to see it presented as a sequence of individual wins and losses. Mostly a problem of convenience. If I want to tell you about what happened in 10,000 games of Hearthstone, I want to present you to this ideally with a single number instead of a list of 10,000 different games and their outcomes. It's simply much easier to digest one number than 10,000 different outcomes. But it's important to realize that the number that we're dealing with here, because it's convenient, is in many respects extremely unnatural for our brain. And it's easily capable of leading us to form incorrect expectations in the short term that harm our enjoyment. And in fact, on that note, it's really easy to understand why so many people get baited by content creators posting about what happened in 10 different games of a deck they played. Because the information in those posts takes the form that our minds expect. And so we might accept that information much more readily than we should. Put concretely here, if you see a streamer posting about playing 10 games and winning 8 of them, this is exactly a natural frequency that our mind can wrap itself around. And so we might say, wow, he won 8 of those 10 games, and now I'm going to disregard the role that chance plays in this because chance is not particularly actionable, and I'm going to conclude, based on my available information, that this deck is actually really powerful. I'm going to go make it. It fits exactly what our brain tends to do, and thus a lot of people end up getting misled because of just that natural synergy between the form of the information and the form of the information our brain expects. But it's important to remember that when you see this type of stuff, you are not seeing the full picture. You're only likely to see people posting about their successes and not their failures. You're receiving a very non-representative sample of information presented in a form that our mind finds naturally appealing. So it's no wonder why so many people get baited and make the incorrect choice.